How does switching frequency impact DC-DC converter design? Imagine trying to tune a musical instrument, where the pitch changes depending on how tight the strings are. In power electronics, switching frequency is like that tuning knob, shaping how a DC-DC converter performs. When engineers design these converters, they have to think carefully about how fast the switches turn on and off. This speed, called switching frequency, directly affects the size, efficiency, and stability of the system. Higher switching frequencies allow us to use smaller magnetic components like inductors and capacitors. This means the overall converter becomes more compact, which is perfect for portable devices or space-constrained renewable energy setups. Smaller components also mean lighter weight and better power density, making the system easier to integrate into various applications. But there is a catch. As the switching frequency increases, the power transistors, often metal oxide semiconductor field effect transistors, or MOSFETs, lose efficiency because each switch transition wastes energy. These losses generate heat and can reduce the lifespan of the components. To counteract these losses, engineers use advanced switching techniques like zero-voltage switching. This method ensures the transistor switches when the voltage across it is near zero, greatly reducing energy loss during each transition. This allows for higher switching frequencies without sacrificing efficiency too much. But higher frequencies also influence how the converter responds to sudden changes in load or input voltage. Faster switching can improve the transient response, meaning the converter can react quicker when the load suddenly increases or decreases. However, it also makes the system more prone to electromagnetic interference, or EMI, which can cause noise in sensitive electronics. Designers often balance these factors based on the application. For example, in renewable energy systems like solar inverters, they might choose a moderate switching frequency to keep losses low while maintaining good efficiency. In battery-powered devices, they may lower the frequency at light loads to conserve energy and extend battery life. They also consider the cost of components, as higher switching frequencies requiring more precise and sometimes more expensive parts. In summary, switching frequency impacts DC-DC converter design by enabling smaller, lighter components and better transient response. But it also increases switching losses and electromagnetic noise. Finding the right frequency involves weighing size, efficiency, thermal management, and electromagnetic compatibility to meet the specific needs of each power system.